One, two, three, four. So you can tell it's working in the other room? Hmm. Okay.
One, two. Yeah, there. Okay, there you go. Good. Yep. No, it shouldn't. If it didn't all afternoon yesterday, then. That's analog.
Testing, testing. One, two, three, four. He's tinkering. Testing, testing for Alex. One, two, three, four.
The last session, I could hear a tiny bit of distortion in the other room.
Hmm.
I mean, it wasn't bothersome or anything.
On the voice?
Yeah.
Yeah.
So, well, it might have been the computer feed, might have been the volume, might have been up a little
It,
too.
it sounded a bit echoey in the
It's
other
going to
room.
sound echoey just because this room
Oh,
is.
I mean in the other room.
Well,
Oh, I see, I see.
it's picking
Yeah,
up.
yeah, 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 yeah. Makes sense. Yeah, got it, got it. Yeah.
And it's, like I said, it's much worse. just going to go outside. Start.
Okay, well, let's go ahead and get started. So I'm honored to introduce our keynote speaker today, Jose Jimenez. Jose is a professor in the Department of Chemistry and Biochemistry at the University of Colorado in Boulder and is also a fellow at Ceres. Jose's research focuses on the development and application of instrumentation for measurements of the chemical composition of submicron aerosols and gases. And he really has a reputation for working at the cutting edge of instrument development and their application. And these instruments that he is developing are used in field studies, in lab chamber and reactive studies, and reactor studies. He's a fellow of AAAR and AGU and is a highly cited researcher according to several different metrics. So, Jose.
Thanks, Becky, for the introduction, and thanks, Danielle and the steering committee for inviting me. I've always been, I'm an experimentalist, I'm mostly not a modeler, but I've always been fascinated by models and their ability to extrapolate and the implications and the interactions of what we think we know and compare that with measurements. So I'm always talking to people like Danielle and Colette and Jenny Fisher, and thankfully they put up with me. Anyways, I'm gonna give some things that I think would maybe be useful for this audience. Okay, and I'm going to be following this outline, in which I'm going to talk first about acidity, and then we'll focus on organic aerosols. So first, acidity, so as measured by pH on the x-axis. I think I need 3 hands to handle everything. So here we see a number of aerosol processes that depend strongly on pH. So for example, oops, it's not going to work. The manual way. Okay, so we see here, pointer is pretty weak. Okay, we see here examples. For example, the aerosol formation from isoprene that Paul Wember talked about yesterday, that is enhanced at very low pH, and the partitioning of ammonia that favors the particle phase as you go to very low pHs, and on the other hand, the partitioning of nitric acid favors the aerosol at higher pHs. So then. And I'm going to show some data. There is some data over the continents that show that the pH over the continents is typically about 1 to 2. And we are lucky that we have some data from the NASA Atom project shown here, where we're going to fly this circuit 4 times, and we've already flown it twice. A very useful project. And because you have the DC8 full of instruments, and 1 week you are here, and the next week you are there, and you have a consistent payload measuring the remote atmosphere everywhere. So these are the results that we get for pH across. So these are now the vertical profiles, and this is the map. And what you see is basically you see red colors almost everywhere, except in a few places the pHs are actually lower than 0 in the remote troposphere. This surprised me. Maybe it shouldn't, but it did. So then this is now the distribution, the histogram of the distribution of pHs that we estimate. This is using the AIM model, which is similar to Isoropia, which is inside of GeoScam. So the pH is mostly lower than 0 in the remote atmosphere. And so you would expect, for example, that the nitrate would be all in the gas phase because the pH is so low. And indeed, that's what we see. The nitrate is the nitric acid goes to the gas phase, and then it reacts. When nitrate is seen, it's basically in the supermicron aerosol, which is less acidic. So it's consistent with that prediction. So now we look at GeoScam version 9, what the pH that it predicts for this same track is low as well, but it's actually about 1 unit of pH higher. Okay, so this may have some implications for some of these processes. So the summary, the aerosol is very acidic, and one thing I don't have time to show is that the ammonia seems to be lower. In the ammonia that we expect from the observation seems to be lower than what GeoScam is predicting, and that may explain some of the difference. So I'll switch gears to organic aerosols. So as a quick introduction, this is a map that we published some years ago with measurements over the continents. And really the take-home point is that the red, which is the sulfate, and the different flavors of green that are the different secondary organic aerosols are comparable across all the continents. And this led to a lot of work trying to better understand and model secondary organic aerosols. And this is as part of that work. This is a study that was published by Kostas Sigaridis a couple of years ago, where he compared 25 different models, and this is the vertical profile of organic aerosols over the Southern Ocean. And this is a log scale spanning 6 orders of magnitude, and the models span about a factor of 1,000. Not great. If you wanna, of course, you guys care about geoschem, so I'm highlighting 2 versions of geoschem that participated that tend to be on the higher end of things, to be expected since you guys pay more attention and incorporate more of the sources for organic aerosol. And I'll come back to a comparison with data at the end of my talk. But that's where we are in terms of the overall modeling community. So I'm going to touch on 3 different sources of organic aerosol and some things I think we should do in the models and not do. And then I'll show some global comparisons. So first of all, the easy one is this SOA from the isoprene epoxide that Paul and Kelvin Bates touched on yesterday, in which basically you have isoprene, it oxidizes to make this epoxide and a million other molecules, but this is the important one. And then it's taken up into an acidic aerosol and then forms these molecules and also some oligomers. So, people ask, should I put that in my model? And the answer is definitely. This is some independent evidence in which we showed, so this is now a map of IEPOX predicted by Fabian Paulot using geoschem. And you see that this is the gas phase species. This is expected to be there when there is high isoprene and low NO. And now if we look at places where in some cases there is isoprene, but there is higher NO, like in these studies, the pie charts show all gray, meaning we cannot identify this type of aerosol in our measurements, even though it has a very distinctive mass spectrum. Now, when we look at places like the Amazon, Southeast US, Borneo, it's always there at a substantial concentration. It explains, a third, a quarter of the organic aerosol that's there. So you should always put this mechanism in the model, and you guys are lucky that the Caltech group is already doing some of the work, and Eloise Murray has already implemented a version. Also, it's important to know that even in regions that you have a lot of isoprene, like the Amazon or Borneo, it's not the whole story. Some reviewers were recently surprised. It's like, how come it's not the whole thing? It's like, well, there are many other important sources in those regions, in particular monoterpene, so I think is quite important. I won't have time to say why. Anyway, so that was the easiest one. Next, I'm going to talk about formation of secondary organic aerosol from pollution. And I'm going to use this paradigm in which we're going to study a megacity in which we have relatively cleaner air, and this may be LA or Seoul or Mexico City or different places. And then as the air is advected, we have photochemical aging and dilution. And we're going to use this formulation to try to understand the data. So we're going to plot the increase in organic aerosol divided by the increase on the excess CO of the background, and that's to correct for dilution. And we are going to plot that versus photochemical age. And the projector doesn't show at all. Well, you have to believe me, there is a wedge here. This is the primary organic aerosol, and then there is a gray wedge here that has disappeared, which shows with the secondary data from Mexico City and the Northeast US we're showing. And then this data from Los Angeles is consistent with that, and then these are several recent field campaigns. So this is the winter, the blue points are the winter campaigns that was discussed by Liat and will be discussed by Viral later. This is some recent data from Seoul, and this is data from the outflow of China. So you see, you always have relatively low primary organic aerosol and a growth of the secondary organic aerosol on a time scale of about a day. And we also know from, you tend to plateau, but we also have better observations. For example, this is from an aircraft, and this is from a flow reactor in LA, that things seem to plateau after about a day. Okay? And we see some version of this about everywhere. And this is what underlies this simple parameterization that was discussed yesterday. So now the same data shown in a log scale, and I apologize, this got scrambled. So you see here, this is the formation. And then it also matters what you do at long ages. This is what we see in the flow reactor, is that if you expose the air to a lot of OH, eventually you chew up the organic aerosol with a time scale of a couple of weeks. And this is going to matter, that time scale is going to matter a lot for what you see in remote regions. So I wanted to also encourage people to always, when there is a possibility to use tracer correlations or normalize things in this way, to always do so, even if you're looking at a model. And look at your model output as if it was data. Okay, and for example, I'll show an example in which we collaborated with the CIMAC group at EPA, And when they plot their concentrations of SOA predicted for Los Angeles, and this was an update supposed to close the gap with the observations, they were low by a factor of 5.2. So it's like, the observations are still much higher, what's going on? But what we showed is by analyzing it in this way, is that now this is now the model, now the observations, and the model had this slope, and the observations had that slope. So the intrinsic formation efficiency of the mechanism they have there was only low by a factor of 1.8. And what was going on, we were able to show independently, is the photochemical age was too low, OH was too low in the model by about a factor of 1.5, and they either had too many emissions or too low emissions or too high dispersion by a factor of 2. Okay, so I really encourage people to try to use these frameworks to try to separate what the different things that may be going on with your model, and I think much more of that should be done. Okay, one other thing I would say in this context of the SOA parameterizations, and I think there is some version of this in some version of GeoScam, but basically, so you start with one precursor, this is a volatility scale, and it gets oxidized and it makes some other lower volatility precursors that then partition to the aerosol to some degree. So when this was put into models, this is what happened. So this is a fit to the observations like the one I showed before, and these models were coming up too low. So people like Spiros Pandis said, well, let's get these guys and keep them oxidizing and oxidizing and oxidizing, and as Neil Donahue said, use like a zombie marching towards the aerosol. And when you do that, you get something like this. And over an urban area, given all the uncertainties, it tends to actually work pretty well. And if you only have data over urban areas, we've solved the problem. But it has a big problem when you now look at larger ages. This keeps marching and marching, and the zombies keep arriving, and then you end up with way too much aerosol over regional scales. Okay? And this is a problem in a lot of the literature, and it's often unrecognized. So in terms of my recommendation to how to represent pollution SOA, it's actually similar to what was discussed already, so I'll be brief. I think if you care about it, then you should use updated parameterizations. This is one where we have used all the observations we could to constrain it. And if you don't care about the details, you study mercury or halogens but want to have the right amount of aerosol, use this simplified parameterization that was discussed yesterday. Okay, so I'm going to touch now on SOA formation from biomass burning aerosols, and we're going to use the same framework as before. So we're going to normalize the amount of organic aerosol in the air as we crisscross it with an airplane, for example, by the amount of excess CO, and plot versus photochemical age. And this is data from a paper 6 years ago where we summarized the available aircraft studies. And you see this is very different. This is now the urban aerosols for comparison. In the urban case, you start with low primary aerosol and then a factor of 10 more secondary aerosol with a time scale of about a day. In the biomass burning case, it's very different. You start with high levels, and then often it's flat. Sometimes things increase, sometimes they decrease. And we recently did, as a part of our review, we updated basically this database, and basically you have higher numbers, but it's the same result. Out of 17 studies, 10 are flat, 4 see some increase, 3 show some decrease. So basically, you don't see a lot of formation of addition of organic aerosol in biomass burning plumes, even though this has been seen in some chambers. And so I think people should also be careful with this. There is a study here in which they took one of these zombie mechanisms that seemed to fit some chamber study and had been proposed, but when you put that in the model, it is making more and more and more aerosol. And so you go from estimates of global organic aerosol from this biomass burning SOA, from these relatively low numbers in teragrams per year, to it being the largest global organic aerosol source. So I think it's, again, something. So it's good to pay attention to the chamber studies, but I think if the chamber and the field studies conflict, we should respect the field studies. And finally, I'll talk about some of these results from the ATOM project about what we see for global OA in the remote troposphere. So this is vertical profiles from ATOM 2, so the second leg of ATOM, from going from south to north, and this is the Pacific basin and the Atlantic basin. So you see concentrations are often quite low. We have more aerosol here in the equatorial and northern mid latitudes, but still generally low. So how does this compare with GeoScam? So here we have results from version 9.12 run by as a part of a paper with Alma Hodzic. And then this is how that standard version does. So you see that in many places it seems to overpredict by quite a bit. Okay. And this is, as was discussed yesterday, this is a version that is too low compared to the observations in the source regions. So what Alma did in this paper was add some of these sources from isoprene that we discussed yesterday and some other sources. And then if you just add the sources and keep the removals the same, then you end up with this. So you end up over-predicting even more. And what she did next, and this was before these data were available, is to say, well, we also think these removals that I mentioned earlier by heterogeneous chemistry, but also maybe photolysis and where the position may be more important or maybe faster than are represented in the model. And when you do that, you end up with this red line, which approaches the observation more. So this is no doubt not the only error or difference between the model and the observations. This is still very preliminary, but I think there is something to that, and the removals need to be faster than in the default version. Okay, and that's just the summary of what I said. Okay, so I'll leave the conclusions there, and hopefully I left time for some questions. Thank you. I don't really know, but this is some of the plots we've been making. So this is now the ammonia in geochem, and this is the ammonia that we estimate by running EAIM on the observation. So with a very high acidity, we find that basically there should be no ammonia in the gas phase. Geochem has more ammonia, but the discrepancy is more higher up than close to the ocean. So. Okay. We should talk.
Maybe as a following question, what are the concentrations of the cations in the observations in the model that might impact pH?
So the ammonium is also a little higher, but the ammonia shows the more stark difference.
For the oxygenated waters, because beyond those bounds, basically water dissociates spontaneously, right? So what does it really mean, negative pH? Can that really happen in the atmosphere?
It can, according to the models. I mean, I think it just means the concentration of hydrogen ions is like, I don't think it's unphysical. I mean, I'm not an expert on the subject, but you see papers from physical chemists where they use negative pH. I mean, it just means that log of the concentration. So it just means a very high concentration of hydronium ions.
Yeah, I have a question about the kind of a sampling bias of your observation. Because when you do the aircraft scans, you tend to measure the atmosphere, presumably in very clear sky conditions. Do you guys try to avoid like deep clouds, or how representative are do you think they have a little of the sampling bias for clear sky?
So, I mean, I think that's one nice thing about the Atom data set is that they're really trying to do this as long as it's safe. Basically, if it's not unsafe, we will fly and we are not looking for plumes. A lot of the other campaigns, you are targeting the pollution and using models to try to find the pollution and sample it more, like some of what I showed for the biomass burning or whatever. So those are really trying to crisscross the pollution. Campaigns like this are trying to be as unbiased as possible. If there is a dangerous deep convection cloud that we avoided, although we've done a study trying to fly around deep convective clouds that we could discuss offline.
So for the ammonia slide you showed, are those measurements took over the clear sky days, or?
That includes everything. I should say none of these are measurements. The ammonia from the measurements is using the model because we don't have an ammonia measurement, so it's using the model and the nitric acid and the aerosol concentrations to estimate the ammonia. And this is the ammonia when we do the same with geoscam.
So you showed those comparisons with ATOM for organic
Yeah, I mean, there is a lot of information more than we have digested, but here you see the top is geochem with the usual AMS colors, red is sulfate, and this is the bottom of the observations. Okay, so there are some differences as well in the other species which I haven't discussed. And there is no doubt also some errors of transport, so I shouldn't say not everything here is errors in the mechanisms or differences.
In terms of the differences between the evolution of the urban plumes and the biomass burning plumes, do you suspect that the differences in the relative dilution rates, with fires being a smaller plume where the CO and the OA is dropping, causing potential evaporative effects, where urban plumes may be bigger, or do you think they're more comparable in size and that wouldn't explain differences?
I mean, the urban plumes are often more diluted in the sense that, yeah, but biomass burning plumes vary a lot. I mean, some of these studies are, you know, an agricultural fire, and others are like fires that you are crisscross. It takes half an hour to cross the plume, and then you come back in half an hour. So I don't get a sense of scale is the critical parameter.
One more question for Jenny. So you showed those pie charts of the contributions to organic aerosol in different places around the world, and that the isoprene-derived SOA is only about a quarter to a third. Does that mean that we really need to be thinking about what we do with monoterpenes more carefully?
Yes, I think I didn't have time to include it, but monoterpenes, I think there is a lot of emerging evidence that even in places where isoprene is large, monoterpenes is at least as large a contributor. Anyway.
Let's thank Jose again. So our next talk is by Crystal Weigel from Dalhousie.
Okay, so thank you all. Before I begin, I would like to thank and acknowledge every single person on this list for their outstanding contributions to this work. Fine particulate matter is a known robust indicator of increased mortality and morbidity. The global burden of disease estimates that over 4 million premature deaths are attributable to PM2.5 exposure each year. In addition to these health effects, the costs associated with PM2.5 exposure are estimated to be approximately 3% of global GDP, and this is just expected to grow over the coming decades. GeosChem offers a powerful tool to interpret and look at the global distribution of PM2.5. However, there is a lack of a global monitoring network that can be used for evaluation. To address this need, we've developed the Surface Particulate Matter Network, or SPARTAN, that measures ground-based PM2.5 co-located with Aeronet AOD measurements. All of our analysis is completed using standardized methods, including weighing in a clean room facility that follows US EPA protocols. Here, I've shown the location of SPARTAN monitors, as well as some examples of excellent agreement with independent measurements. This includes for mass, composition, and trace metals that we use to infer dust concentrations. We use GeosChem to interpret initial measurements from SPARTAN to look at in sites that are in highly populated regions that are relevant for health. One of the first things we've discovered with SPARTAN was a lack of an anthropogenic dust representation in urban areas, and this was signified to us by elevated zinc to aluminum ratios. Work by Sujeev Philip, who is somewhere here in the audience today, has shown that including anthropogenic, fugitive, combustion, and industrial dust increases agreement across all SPARTAN sites. In addition, including this anthropogenic dust inventory also decreases the low bias in PM2.5 mass by approximately 10% and also increases global population-weighted PM2.5 by about 3 micrograms per meter cubed. This study is an example of how we can use SPARTAN measurements to investigate the bias in PM2.5 from GeosChem. Here I show the annual mean concentrations of major chemical components as simulated by GeosChem with overlaid circles showing the location and value of SPARTAN measurements. We can see that the simulation exhibits skill in reproducing the concentration and spatial variation of major measured PM2.5 components at SPARTAN sites. Correlations are generally above 0.6, with the exception of black carbon, which is known to have highly heterogeneous sources. We see a high correlation for sulfate and ammonium, showing that the model shows excellent skill in reproducing these concentrations as well as spatial variation. However, a low slope for sulfate does imply a low bias. The high bias shown for nitrate is largely driven by a large overestimation over East Asia, but elsewhere it compares really well. We see a low slope for organics, and this again implies an underestimation of this primary organic component. However, this is consistent with other previous studies. The dust simulation has benefited extremely from the dust inventory from Davin's group. However, we do see a slope above unity, which does signify a high bias. Here I show a plot in the upper left corner that is showing you the relationship between satellite-based PM2.5 and geoschem PM2.5. We see a high degree of spatial variation. However, a relationship generally below 1 signifies that the simulated PM2.5 is too high over these dust source regions. When we compare the Spartan measured speciation to that simulated by geoschem at 2 arid sampling sites located in Rehoboth, Israel, and Alora, Nigeria, we see that this high bias is largely due to an overestimation in dust, whereas all of the other major chemical components compare fairly well. This implies a need to further reduce these dust concentrations over source regions. When we scale global PM2.5 as simulated by geoschem to satellite-based estimates, we see a decrease in bias. However, more importantly, we see a dramatic increase in the spatial correlation between simulated PM2.5 and Spartan measurements. We use this PM2.5 scalar from satellite-based estimates, along with geoschem, to investigate the contribution of 7 source categories to Spartan measured composition. So on this plot, I'm just showing one example from one of our sites located in Hanoi, Vietnam. And on the far left, we see the Spartan measured composition, whereas the other groups of bars are showing the composition from various source categories. So generally what we can see here is that the measured speciation supports the source apportionment from geoschem, showing that we can use geoschem to understand the sources at Spartan sites as well as globally. Here I've shown some global maps of PM2.5 from geoschem. So in the upper left, we have the total PM2.5, whereas the other maps are showing the contribution from 7 source categories. We find that natural sources contribute the highest to total population-weighted PM2.5, and this is largely driven by mineral dust as well as a diffuse background from emissions from biogenics as well as sea salt. Residential energy use is the highest contributing anthropogenic source category and contributes approximately 20% of the global population-weighted PM2.5. This is largely due to the widespread use of solid fuels for domestic cooking and heating in highly populated regions, such as in Southeast Asia, as well as over many parts of Africa. We see that industry and power generation combine to contribute about 30% of the total population-weighted PM2.5. Excuse me. And this is largely due to exposure over industrialized countries as well as emerging economies. Transport, agriculture, and biomass burning combine to make up the remaining 20% of population-weighted PM2.5. In summary, emerging measurements from Spartan offer new insight into the geoschem simulation of PM2.5 composition as well as mass. Furthermore, geoschem is an extremely powerful tool for investigating the global distribution of PM2.5, especially when constrained by satellite-based estimates and ground-based measurements. Thank you all so much for your attention. I'll happily take any questions.
Questions for Crystal?
You may have already said this and I missed it, but what do you use as your emission inventory where there are no regional inventories available?
We use Edgar version 4.3. Oh, excuse me.
So I see there's a lot of natural dust all over the world. I wonder what they will be. It's not like it's not dust storm.
So there are natural dust emissions from various deserts. So there's the Gobi Desert. There's emissions also from Australia. We see also high dust measured at our site in Buenos Aires, Argentina, as there is a dusty region just west of that sampling site. So it's coming from a lot of different places. And transport also from the major desert in the Sahara. Oh, so this is natural sources and not just dust. So this would include emissions from biogenics and also sea salt, any sort of natural emissions. Thanks. Thank you.
Thank you. Okay, so our next speaker is Prasad Kasibatra.
Thank you all. All right, I'm going to talk about some recent work on source of HONO and NOx from sea salt nitrate photolysis. So before I start, let me just thank people who've been so patiently helpful, Becky and Kanji, Paul, Matt and Chris, and Alma Hodzig at NCAR, and of course the awesome Geochem support team. Melissa told me yesterday she'd be coming into work last few months and find all these questions from me every day. So thanks, Melissa and everyone else. I'm going to start by just showing a couple results. So a couple of papers that were recently published. One by Yi et al., which looked at measurements of HONO, NOx, and particulate nitrate in the marine boundary layer off the southeast coast of the US from 2 flights in the NOMADS field campaign. And they reported measurements of HONO, which were pretty high, about 10 parts per trillion, in air that they considered was aged marine air. NOx about 25 parts per trillion or so, and particulate nitrate about 50. They did a box model analysis and found that to explain the levels of HONO that they were seeing, they needed a source that was correlated to the product of particulate nitrate times the photolysis rate of nitric acid, with the slope of this line being about 300. And so they argued that photolysis of particulate nitrate is about 300 times, the rate constant is about 300 times the rate constant for the photolysis of gas phase nitric acid. Matt's group recently reported longer-term measurements from a surface site in the tropical eastern Atlantic, and they focused on the diurnal cycle of NOx, which is in this black line here, and they see this very distinct cycle, diurnal cycle with a peak during the day. They did some box model analysis, and that's the dashed line here. They cannot reproduce that diurnal cycle with their standard box model. Among other things, they did some further analysis, and among other things, they needed a photolysis source of particulate nitrate here to explain the diurnal cycle. This is their dashed line with particulate nitrate photolysis, among other things. You can also see a stronger pan-diurnal cycle. And you also need that to explain HONO, which is their orange line here, which you can't without this particulate nitrate photolysis. Their estimated particulate nitrate photolysis rates were about 10 times the gas phase photolysis rate. So I wanted to look at this in Geochem. I thought it would be pretty straightforward. I used version 1101. Just a reminder that it just has tropospheric bromine chemistry. I corrected a couple of bugs related to acid uptake on sea salt aerosol, added photolysis loss of NITS scaled to JHNO3, and I'm going to show 4x5 simulations for 2013. I've checked some against 2x2.5, but I'm going to show mainly 4x5. Okay. The first thing that jumps out is this. I looked at how the model does in terms of actually reproducing measurements of particulate nitrate and nitric acid. The black here are the observations, the red are the model, the circles are gas phase nitric acid, and the squares are particulate nitrate. The Cape Verde measurements, most of the nitrate in the marine boundary layer is in the particulate form. It's about 10 to 1 the ratio. The model is exactly the opposite. And that story plays out. These are measurements from a ship cruise, a latitudinal transect in the eastern Atlantic. This is near Cape Verde. This is near the ITCZ in the South Atlantic. And again, in all these regions, most of the nitrate is in the particulate form. In the observations, in the model, it's in the gas phase. You look at a map of model surface nitric acid and NITS, and you can see that most of it is in the gas phase. And the reason for this is pretty simple. In the model, nitric acid uptake on coarse mode sea salt aerosol is limited by alkalinity. you do a back of the envelope calculation, you look at typical sea salt aerosol emission fluxes, convert that to equivalents, will imply a NITS production rate of about one couple of ppt an hour. Not enough to explain the 100 ppt or 100 to 200 ppt of NITS, particulate nitrate that is in the observations. Okay. And in the model, actually, it's even less because there's also competition for the alkalinity with SO2 uptake. But there's lab and field measurements that shows that there's continued uptake of nitric acid on sea salt aerosol by hydrochloric acid displacement. And so I updated the uptake. And what I did essentially was to call isoropia a second time to calculate the nitric acid equilibrium concentration associated, gas phase equilibrium concentration associated with sea salt aerosol, and then use that difference with ambient and this equilibrium concentration as a driver in a mass transfer formulation. Okay. You do that, and things change dramatically. Okay. Something went wrong with that. Okay, so now you can see that the model reproduces this pattern of most of the nitrate being in the particulate phase. In fact, it seems to push a little too much nitric acid into the particulate phase. And that's true near Cape Verde and also with these ship measurements. And if you look at the model now, you can see that now there's quite a bit of nitrate in the particulate phase. And in fact, in most of the ocean basins downwind of the continents, now the model shows particulate nitrate being in the particulate phase as opposed to the gas phase, consistent with some of these observations. Okay. So I then used this updated model to look at the effect of photolysis. I did runs with a series of calculations where I scaled the NITS photolysis rate to nitric acid. Black is 0, and then I went 10, 25, and 50. This is the NOx. The black here are the observations. And you can see that somewhere between 10 and 25, with a scaling factor of 10 and 25, you start getting the seasonal cycle, the diurnal cycle, but you don't fully capture the diurnal cycle. The model has a much broader peak. Now, I have to say that all these solid lines are with a debromination from sea salt aerosol, which is twice the standard. The dashed line is the standard there. And the reason I did that was if you look at the BRO measurements, the model significantly underpredicts BRO in the marine boundary layer. Doubling that source improved it a little bit, but still significantly off, reduces the NOx a little bit. Okay. For HONO, again, with a scaling factor at about 10 to 25, you start getting the diurnal cycle, but you still significantly underestimate the peak, which is at about 3.5 parts per trillion. One thing I did was in this model, there's this strange bump at night, and that is because of heterogeneous HONO production from NO2. I took that out, and that's what that shows. And you can see what ozone does, again, between 10 and 25 is something that you need to explain. Yeah. Okay. What is it in terms of impacts? Ozone changes by a few ppb when you add this particulate nitrate photolysis in. It's about 10 to 12% in terms of ozone change in the marine boundary layer. OH change, the percentage is about 15 to 25% or so. So here are my conclusions. This updated calculation of nitric acid uptake on coarse mode sea salt aerosol, I think, improves the simulation of nitric acid particulate nitrate partitioning in the marine boundary layer. Including the particulate nitrate photolysis partially improves the simulation of these diurnal cycles, but not fully. Leads to an increase of about 10 to 15% in simulated ozone, 15 to 25% in OH. But I think the next step really is to couple this with all the work that's been done on halogen chemistry, especially the Chauvin et al. Paper, which I think has the most comprehensive halogen chemistry right now. Couple this with that and kind of then look at it much more comprehensively. So thank you.
Why did you describe this additional displacement of chloride by nitric acid using a kinetic expression rather than an equilibrium? I think isoropia, does it not handle this?
Well,
it's chlorine as an additional species. Would it do that for you?
It does, but the uptake is diffusion limited.
Is it?
Yeah, and so I wanted to make sure that this captures it. I mean, if it gets to equilibrium, this will just get to equilibrium. right? But this is a mass transfer relationship, with the driving force being the difference between the ambient and the equilibrium. And so in the coarse mode, you may not get to equilibrium because of the diffusion limitation. Thank you.
So our next speaker is Viral Shah from the University of Washington.
Thank you, Becky. I'd like to begin with acknowledging my collaborators on the winter campaign. So winter campaign, we were in the Northeast US in the winter of 2015. One point to note is most of our observations were below an altitude of 1 kilometer. We are very close to the surface most of the time. I'll be looking at submicron aerosol concentrations, interpreting them with the geoschem model. So let me begin by why this is an interesting topic. So we know there are large differences between winter and summertime concentrations. Wintertime aerosol concentrations tend to be lower. This is the Northeast US. There's less of a biogenic component, and there's a partial shift between sulfate and nitrate because of changing photochemistry and thermodynamics. In the past decade or so, because of decreasing SO2 emissions, sulfate concentrations have decreased drastically during the summer. But the winter, not so much, and there's a diverging trend. It seems the wintertime concentrations tend to be higher now than the summer. Now, this is interesting. Moreover, Hawala Pai and co-workers have shown that the wintertime concentrations may actually increase slightly by 2050 because of changes in emissions alone. So all of this makes wintertime aerosols over Northeast US a very interesting topic. Getting back to the winter campaign, I'm using a version 10.01 nested grid, half a degree over North America, with a few modifications. First is I use a simplified OA chemistry as described by Colette yesterday and Jose earlier this morning. We assume the POA to be non-volatile, and it gradually ages to form SOA. SOA is also formed from the oxidation of semi-volatile organic compounds, and for biogenic SOA, we assume a simple yield from isoprene and monoterpene. Second, we introduced the transition metal ion catalyzed sulfate production pathway in version 10 in the standard model. And there were a couple of more bug fixes, but this is based on the work by Becky Alexander. And what we see is a large increase in sulfate production over the Northeast US with a factor of 3 increase over the Ohio River Valley, which is a source of SO2 and transition metals. And third, we introduced the Bertram and Thornton parameterization for N2O5 hydrolysis and lower the diedeposition, or the resistance to diedeposition to nitric acid, as described by Liat yesterday. We see a much better correspondence in nitric acid compared to the aircraft observations with these two changes. In terms of emissions of SO2 and NOx, we see that the vertical profiles of SO2 and sulfate within the bottom 2 kilometers and that of NOI and particulate nitrate match very well with the aircraft observations, suggesting the emissions and the lifetime of these two species are well represented. For ammonia, it seems the emissions are overestimated by about 50% or so. And we know ammonia emissions are temperature dependent, as can be seen from the seasonal cycle, lower emissions at colder temperatures. It turns out that 2015 was a really cold winter in the Northeast US. And we take into account this cold temperatures by rescaling the seasonality of the ammonia emissions using this empirically derived temperature dependence. And we see in the month of February, the ammonia emissions are a factor of 3 lower than the NEI inventory. When you put this in the model, we see a great agreement between the model and the observation. So the seasonality of ammonia emissions is important to be specific to the year we are simulating. So after making all of these changes, we can look at the model comparison with the aircraft observations. I'm showing the AMS observations from Jose's group and the geochem results here. For sulfate, nitrate, and ammonium, the total concentrations match really well with the observations. The mean bias is about 4%, and 81% of the model values are within a factor of 2 of the observations. We also see a remarkable agreement in the distribution of sulfate, nitrate, and ammonium. And by extension, we also see a good agreement in the pH modeled by geochem. With organic aerosols, we see a kind of a 50% overestimate in the concentrations in the model. This is a very simple scheme. There may be emissions that may be overestimated, formation of SOA. But again, it does reasonably well in terms of the spatial distribution and variation. When we look at the source contribution, SOA versus POA, we find a good correspondence between the AMS positive matrix factorization and the geochem, with both predicting about 60-40 SOA POA in this region. So now, having developed this confidence in a simulation for this period in this region, we can look at the aerosol formation pathways. And we see that about 75% of the sulfate production happens in the aqueous phase. 55% of the nitrate is formed by N2O5 hydrolysis. And almost all of the OA is anthropogenic in origin. I would like to conclude by saying that the processes that we modified or looked at in the model, the transition metal ion catalyzed formation of sulfate, the N2O5 hydrolysis, nitric acid dry deposition, emissions of ammonia, and the OA chemistry, all of them are critical for simulating wintertime aerosol pathways and, for that matter, interpreting the trends. Thank you.
Questions for Viral? Eloise.
Is there enough information from the aircraft observations to split that pie chart into a north and a south? Or is there enough variability between north and south?
Not quite, because we were looking at anthropogenic pollution plumes, and so even if we're in the south, we may be looking at plumes coming from Washington, D.C. and New York, and that's what our target was. So we did not really sample the south.
Jenny.
In your OA comparisons map, it looks like the model was really over-predicting over the ocean and the outflow. Does that suggest something about the timescales for aging we're using in the simple parameterization for anthropogenic SOA?
It could. My first suspicion is that so most of the OA, the POA, is from wood combustion, and biomass burning POA does not produce as much SOA as fossil fuel POA. So we, with the NEI, we are lumping all of it together and maybe forming too much SOA. So that's my first suspicion, but it could be timescales. Okay.
Thank you, Viral. Okay. So our next speaker is Chi Lee from Dalhousie.
Okay. I'm from Dalhousie University, so many of you might know that our group used satellite AOD to infer global PM215 to support health studies. And recently, our group have published research on the 15-year trend in PM215 globally. It is great to know, like globally, there are PM215 increases somewhere and decreases elsewhere, but it's less insightful in terms of sources and processes behind these trends. But if we know more specifically about trends in compositions, that might be more helpful. But observational information regarding this composition trend is only available over limited institutional networks over North America and Europe. So we use GeoScam global simulation to provide a global perspective. But one outstanding issue regarding modeling global PM2.5 exposure is the relatively low resolution, which could introduce biased low estimates of population-weighted PM2.5 over industrialized regions, because the population density is usually correlated positively with the pollution level. So in this study, besides including recent updates in changing emissions, changing met fields, as well as the updates in advanced SOA mechanisms, we also rescaled the original simulation to match the recent 5-year average of satellite-derived PM2.5 in order to reduce the biased estimates of population-weighted PM2.5 over many densely populated regions, such as South Asia. But we also note that this downscaling doesn't modify the original mass fraction of each species or its interannual variation, because we apply a simple scaling ratio to every species and every year. And turns out this simulated trend shows a high degree of consistency with in situ measurements over North America. And we found that the reductions in population-weighted PM2.5 over all observational stations are driven mostly by the strongest decreases in sulfate organic aerosols, and followed by the relatively less decreases in ammonium nitrate and black carbon. The reproduction of organic aerosol decreases is the most significant differences of this study comparing to previous geoscam simulation over North America. And it's benefited mostly from SOA years of aqueous uptake due to the inclusion of the most recent developed mechanism in summer, and also by the inclusion of recently developed organic carbon emissions over other time-varying emissions over other seasons. And not only over North America, we found that our downscaled simulation shows an overall agreement with the global PM2.5 trend in the overlapping years with satellite-based estimates. These two data sources shows a consistent trend and significance level globally, as well as over 15 major global burden of disease studies in terms of the population-weighted PM2.5 trends. And only one small region shows statistically deviating trend estimates. So this promising consistency confirms us to further interpret how different composition determine this trend in population-weighted PM2.5. And I'm showing here the example over the most populous regions around the world. As we could see from the bar plots showing the trend of different composition relative to each other, secondary inorganic aerosols shows significant trends over all the regions, and are all consistent with local trending precursor emissions, and explains more than half of the decreases or increases in population-weighted PM2.5 over these regions. And significant trends in organic carbon emissions and organic aerosols are also important over North America, East Asia, and South Asia. Especially over South Asia, it's not a strange topic. It's not. We are all familiar that residential combustion and organic aerosols are dominant contributor to PM2.5 concentrations over this region. But this study also pointed out that it is also the largest driver contributor to the population-weighted PM2.5 exposure changes in this region. And organic aerosol also has a significant contribution to the increases in population-weighted PM2.5 over East Asia right after nitrate over this region. And the strongest increase in nitrate over this region is driven not only by the continuous increase in anthropogenic NOx and ammonia emissions, but also by the recent mitigation in sulfur emission and sulfate concentration. And because this high contribution of organic aerosols over the two most populous regions, turns out the global population-weighted mean PM2.5 increase is driven mostly by organic aerosols according to this simulation, followed by nitrate because of its high influence over East Asia. And this study focused on health-relevant studies. So we look at population-weighted mean PM2.5 trends. But we also shows that previous studies based on an area-weighted mean approach, the conclusions may not be applicable to be reference of this study, because we found that the area-weighted mean approach provide much weaker global trends comparing to the population-weighted mean cases because of the overemphasized composition effect of decreasing PM2.5 over developed regions, as well as the overemphasized mass fraction of dust influence in the area-weighted approach. So this is what I have about what different composition drives different trends over in population-weighted PM2.5 over different regions. And I'll leave the rest of time for questions. Thank you. Okay, thanks. Thanks. I would like to thank all the co-authors for your contributions to this work. So in this work, we've add one reaction into JustChem, the oxidation of sulfur dioxide by reactive bromine HOBr in cloud droplets. And then we found this reaction is very important for both the sulfur and reactive bromine budgets in the troposphere. So this study is motivated by our previous work that measured the oxygen isotopes of sulfate in aerosol samples that were collected in the remote marine boundary layer from 2 ship cruises. And then in that study, we quantify each sulfate production pathway, and then we found about 33 to 50% of sulfate in the remote marine boundary layer is produced from HOBr, HOCr oxidation, which is a large contribution. So we add this new sulfate formation mechanism into JustChem, the oxidation of sulfur 4 by HOBr. And we use the model version V902 with 4x5 resolution. And we got the tropospheric sulfur chemistry and reactive bromine chemistry schemes from 2 previous studies. And we have some updates on the cloud pH, the alkalinity of sea salt aerosols, and also the bromide recycling on the aerosols. So, so in Smith et al. 2016, the tropospheric BRO column was underestimated when they turned on the sea salt debromination. So they switched off the sea salt debromination in order to better match the observations. But sea salt debromination is the biggest source of BRY in troposphere, although it is uncertain. So in all our simulations,
we always turn on the seesaw debomination. Let me show you some results. This is the fractional change of tropospheric BRY burden after we add a reaction in the model. And the BRY burden decreases by 50% globally, which is a big job. And then we can see a larger decrease over the ocean and also at high latitudes. So for example, over Southern Ocean, BRY decreases by about 80%. So the high latitude ocean is the place where we have a lot of clouds for this HOBR plus sulfur reaction to occur. And also it is the place where the composition of bromocarbons is weak. So we have the seesaw debomination is more important over those regions. And adding the reaction decreases the seesaw debomination rate by competing with the HOBR plus bromide and chloride ions in the cloud droplet and lowering HOBR abundance. So we have less HOBR for the bromide recycling on the aerosols. Now we compare the model results with observations of satellite observations of tropospheric BRO column before and after adding the HOBR plus sulfur reaction. Both simulations include seesaw debomination. And we can see a decrease in the BRO column after adding the reaction, especially at mid-latitudes. The decrease at high latitudes is due to the decrease at mid-latitudes because we don't have the snow source of BRY in the polar regions. And overall, the model BRO column underestimate observations after we add a reaction in the model. And we'll expect an increase in the BRO column if we have the coupling iodine, bromine, and chlorine chemistry schemes in the future. So for the sulfur budget, HOBR accounts for about 8% of sulfate production globally. And this fraction can be higher if we have higher HOBR mixing ratio. For example, over the tropic ocean, the fraction of sulfate produced from HOBR can reach up to 50%, where the HOBR mixing ratio is about 0.6 to 0.9 ppt. And then we can also see the amount of sulfate produced from OH oxidation in the gas phase remains almost unchanged after we add a reaction in the model, which is interesting because there should be less sulfur dioxide to be oxidized in the gas phase if we add a new aqueous phase reactions. The reason why it is unchanged is because adding the HOBR plus sulfur 4 reaction decreases the BRY burden. So we have an increase in ozone and OH concentration. And increasing the OH concentration enhance the DMS oxidation rate, so we have more sulfur dioxide produced. So adding HOBR plus sulfur 4 reaction in the aqueous phase does not necessarily result in a decrease in the gas phase sulfate production and the new particle formation. We really need to consider the impacts of this reaction on the BRY and OH budget, which were not considered before. And I want to show you another aspect of the sulfur-hydrogen interactions in the troposphere, which is the DMS oxidation. I'm adding a couple of reactions into JustChem, both the gas phase and multi-phase reactions, so including the oxidation of DMS by BRO, by chlorine radicals, and ozone. And DMSO is added as a new chaser in the model, and we'll use MSA over non-seesaw ratios observations to constrain the model. Yes, so this is the conclusion. So adding the reaction results in a 50% decrease in the BRY burden, which is initiated by a decrease in bromide recycling in cloud droplets. And about 8% of sulfate is produced from HOBR oxidation globally. Our model underestimates the sulfate production from hogs due to too low HOBR abundance, and we don't have the HOCR plus sulfur reaction in the model yet. And in cloud sulfate production from HOBR oxidation does not necessarily result in less gas phase sulfur dioxide oxidation. Yeah, thanks. Yes.
Which requires sulfur 4. What's the source of sulfur 4 in that region?
Sulfur dioxide. Yeah, the sulfur dioxide dissolve in the cloud droplets, then we get sulfur 4.
Where's the SO2 coming
from the oxidation of DMS, which is emitted from phytoplanktons from the marine biosphere.
How good do you feel about the sea salt aerosol alkalinity that's simulated by the model? We've heard from Jose that maybe the aerosol over the ocean is more acidic than what we have in the model, but maybe that wouldn't apply to sea salt. I wonder, do we have any observational constraints that we can use?
Well, we don't. I don't. There's some aircraft measurement for the sea salt aerosol pH, I think, and also there's some modeling study about aerosol pH. It's about 1, I think, something like that for the accumulation mode sea salt aerosols, and then for the cosmos sea salt aerosol it can be higher, about 5, for example. And then in the model we add additional alkalinity tracer, so we transport sea salt alkalinity.
And our last speaker of the session is Rachel Silvern from Harvard.
So today I'm going to be talking about a really fundamental inconsistency between our thermodynamic theory and observations of aerosols in the eastern US, with important implications for aerosol composition and chemistry. And so we know that sulfate aerosol forms from emissions of SO2, ammonia, and NOx that partition between the gas and aerosol phase following well-established thermodynamic rules. And I'm going to define a few terms that I'll be using throughout this talk. Sulfate in oxidation state 6, and NHX is the sum of gas and aerosol phase ammonium. And I'm going to be ignoring nitrate for the purposes of this talk. So I'm showing on the right predictions from Isopropia, the thermodynamic model that we use in geoschem. And we know that sulfate will take up ammonia quantitatively as ammonium into the aerosol phase until an ammonium sulfate aerosol ratio of 2 is reached. And we can think of 2 different regimes, one in which we have ammonia in deficit, so we're limited by the amount of gas phase ammonia, in which we'll have low ammonium sulfate aerosol ratios and no ammonia in the gas phase. In a regime in which we have ammonia in excess, so we have an ammonium sulfate aerosol ratio of 2, and we expect to have ammonia in the gas phase. So next we can ask, where within this modeling framework does the eastern US sit? And here I'll be showing summertime averages for 2013. So first on the left, I'm showing the ratio of ammonia to SO2 emissions based on our best estimates. And so with a few exceptions of some hot spots of SO2 emissions, we see that throughout the region, we're emitting ammonia in excess of SO2. We can also look at observations of wet deposition, which measure wet deposition of ammonium and sulfate. And we can think of these observations as a proxy for emissions because both aerosol ammonium and sulfate, as well as their gas phase precursors, are efficiently scavenged by precipitation. And we see a picture that looks very similar to the emissions in which we have ammonia in excess of sulfate. However, if we look at aerosol observations of ammonium to sulfate ratios, we see a very different picture. So here I'm showing observations from 2 different surface networks as well as the SOAS ground site. And we see that despite what we know about what we're emitting in this region, we have these very low ammonium sulfate ratios, particularly in the southeast US. And in fact, when we look at co-located sites between wet deposition observations and aerosol observations, we see that even in places where we have a wet deposition ratio well in excess of 2, we still have these very low ammonium to sulfate aerosol ratios. And so now we can zoom into the southeast US where we have these particularly anomalous observations and look back in time to see if we can gain some insight into this departure from thermodynamic behavior. So here I'm going to be showing some regional averages for the southeast US from 2003 to 2013 from observations of wet deposition and aerosol concentrations. And so unsurprisingly, following rapid declines in SO2 emissions, we have significant decreases in sulfate and aerosol sulfate. However, if we look at ammonium, we see no trend in wet deposition following what we know about trends in ammonia emissions over this time period. However, we see a significant decline in aerosol ammonium following at about the same rate as we have a decline in sulfate aerosol. And if we look at the ammonium sulfate ratios, we see in wet deposition observations, we have a significant increase over this time period. Not surprising given that we have an increasing supply of ammonium relative to sulfate. However, if we look at the ammonium sulfate ratio in aerosols, we see that not only do we have a significant declining trend over this time period, but these ratios are declining such that we now have values well below 2 in this region. And this is really surprising given that we know we have an increasing relative supply of ammonia in this region. And so far I've only been talking about the inorganic aerosol components, but we know that organic aerosols are really important in the southeast US in summer. And so because sulfate aerosol has been declining at a much more rapid rate than organic aerosol, we've actually undergone a transition in the southeast US summer from being sulfate dominated to organic aerosol dominated. And in the top left, I'm showing observations of the ratio of organic aerosol to sulfate in the southeast US. And we also know from both laboratory experiments and field observations in the southeast US that we can have a liquid-liquid phase separation between an inorganic salt core and an organic aerosol outer coating. And in fact, one lab study showed that the presence of organic aerosol can actually delay the uptake of ammonia from the gas phase into the aerosol phase. And that's some results I'm showing on the bottom left from that study in which they found that the presence of organic aerosol could actually delay that uptake by up to hours. So in an effort to try to explain the observations that I showed previously, we implemented a simple mass transfer kinetic limitation into Geoschem based on these lab results. So we defined the net uptake of aerosol ammonium as being this rate constant based on the results from this lab study applied to the difference between the local and equilibrium concentrations of ammonia. And so I'm showing some results here. On the left, we have the standard model, which assumes thermodynamic equilibrium. And we see that Geoschem is really over-predicting observations of these aerosols. The background contours are showing predicted ammonium sulfate ratios of about 2. And on the right, I'm showing comparisons in black of the standard model to observations of gas phase ammonia in the southeast US. And we see that the standard model is biased low by over 40%. However, when we put in this kinetic limitation shown in the middle panel, we see that we're able to capture the low ammonium sulfate aerosol ratios in the observations, and we're able to reproduce observed gas phase ammonia without significant bias. And so we offer this up as a possible explanation, but our implementation was very simplistic in nature and is unlikely to be the final word on this issue. And so I'll just conclude by highlighting several implications. So some recent work has suggested that reductions in SO2 emissions would have the co-benefit of decreasing SOA formation. However, if aerosol acidity is not actually decreasing, then that co-benefit may not be as large as previously thought. And then finally, this kinetic mass transfer limitation that we suggest would also have implications for the partitioning of water and other semi-volatile species as well as nitrate. And so thanks for your attention. I'm happy to take any questions.
Questions for Rachel?
Just wondering if your kinetic limitation parameter is a function of things like
So it is a function of the ratio of organic aerosol to sulfate, but not of relative humidity.
You kind of zoomed in there on the last slide on the southeast. What's happening in the rest of the eastern U.S.?
Yeah, so we also show the northeast where we've actually overcorrected the model compared to observations. So I think we would like a lot more information from the lab side, sort of refining this parameterization to be more a function of the organic aerosol to sulfate ratio, where we do have some differences in the northeast US. So we have the same gamma value that we use throughout the region, but we would expect to actually see some differences in reality.
So with this correction, do you still get the right ratio in wet deposition?
In the model? Yeah, so in the model, if we compare wet deposition to the observations, we're doing okay because we're not sensitive to the partitioning between gas phase and aerosol ammonium. So our total amount is okay in the model. It's really the partitioning between the gas and aerosol phase where we have a problem.
So in your uptake coefficient, you consider the effect of the ratio of the OA with sulfate.
Mm-hmm.
Do you consider nitrate and ammonia in there also?
Yeah, so as I briefly mentioned, we've largely ignored nitrate in this work because in the southeast US in summertime, nitrate only accounts for about 4% of PM2.5 mass, so it's not a large contributor. Whereas if we were interested in some other seasons or regions, nitrate would certainly be more important.
Should we move away from an equilibrium-based vision of what's going on in these aerosols and go on to a kinetic for everything?
Yeah, that's a good question. I'm not sure, I guess it depends what kind of question we're asking. Certainly, we're in a situation in the southeast US where we've had such a large decrease in our anthropogenic emissions, and we're really sort of finagling with these details, but in more polluted regions, our equilibrium assumptions may be doing okay.
Let's thank all of our speakers again from this morning.
So, thanks, Becky. Becky, thank you very much for chairing this session. And before we break, let me remind you, what? What?
Posters. Poster Okay, so Danielle, we'll come back to him in a moment. First, let's do poster introductions. If you're presenting your poster, please come up to the front here. Who's first?
Sorry.
I thought you were kicking me out because I was doing a bad job.
He was just saying that.
You're starting, I think, right?
Okay.
Wait till this is done. Yeah, maybe we'll wrap around back there. Get by.
30 seconds, eh? Good morning. The Asian tropopause aerosol layer is a buildup of aerosols in the upper troposphere associated with the Asian monsoon. What is its origin? What is its composition? What is its impact on regional climate? We've been characterizing the atoll with the optical properties with Calypso observations. We've been running GeoSchem to get a handle on the composition, and because there are so few observations, we've gone out and made our own observations from balloons. So come see my poster.
All right. Do you guys suffer from using AOD? Does it leave bad taste in your mouth that you don't know why your model agrees or disagrees with the data? Well, suffer no more. We have this new solution for you. It's called Catch. Basically, what Catch does, it takes GeoSchem data and generates the same aerosol types as you see from the satellites. So when they'll forget about AOD, forget about vertical extinction, what you can actually do is to look at the three-dimensional vertical aerosol types that you can generate from GeoSchem. But wait, that's not all. Now you can also do the chemistry from the satellites.
So mass scattering efficiency relates mass to the optical properties that drive radiative forcing and extinction is observed by satellites. So we evaluate the simulation of mass scattering efficiency in GeoSchem using co-located measurements of scatter and mass from approved network sites. We find a 30 to 40% bias in mass scattering efficiency that is reconciled by increasing the size of sulfate and organic aerosols. This results in an overall increase of up to 40% in mass scattering efficiency over North America.
Hi, I'm Sam from Emory University. We're using the aerosol vertical profiles produced by GeoSchem to scale the column fractional AODs from Miser to get the lower air level fractional AOD values. Then we developed the statistical models to predict with these lower air fractional AODs of Miser to predict the ground level concentrations of PM2.5 speciations like sulfate, nitrate, organic carbon, and elemental carbons. So welcome. Okay, sorry. Well, my poster is at B5.
So the Richard Xu cannot come because his family just had a baby a month ago. So I will be presenting this poster on his behalf. We are looking at the future satellite, called Clario. It will measure the high spectral radiance with most accurate, with high accuracy. And we looked at its potential to constrain the size-dependent dust emissions in GeoSchem. So welcome to poster B.6.
We created a observational operator for Calliope L2 extinction profiles, and this allows us to optimize the initial conditions for aerosols and precursor gases to get a globally consistent 3D distribution, and we can get vertical and horizontal information. So come by and see the details about that.
I'm Kohei Ikeda from NIS Japan. We implemented a tagged black carbon simulation with detailed source region for Asia into GeoSchem, and we examined transport pathway and transport efficiency from individual source region to the Arctic, with a focus on East Asia, North America, Europe, and Russia. We also quantified source contributions to the Arctic BC.
Hi, my name is Jessica Haskins, and I'll be presenting some observations from the winter 2015 aircraft campaign, including some observations of various halogens like HCl, showing some evidence for the widespread displacement of acid displacement of HCl, and also looking at isotropia's ability to correctly predict the chlorine partitioning and simultaneously the nitrate partitioning. So if you're interested in some of the heterogeneous halogen chemistry, you can come check out my poster.
Thank all of our poster presenters. And Danielle.
Okay, a second try. Sorry, with all my apologies to the person. I just want to say, so we're going to break until 10:50. Plenty of time to enjoy the conversation, enjoy the coffee, enjoy the posters. And I want to remind you that we will have our group photo at 11:50, right after the second session. So please don't disappear at the end of the second session. We will be led to very close by to on the law school yard
where a picture will be taken. Just stick around and you'll see a movement in that direction. Just follow. And let's try to do it quick so that we can have ample time for lunch. So thank you very much, and see you at 10:50 for the aerosol microphysics session. Thank you. No problem. Smooth.
Yeah, went well. Everything
Hello. Okay, it's working. All right. So satellite measurements provide valuable aerosol information on a global scale. However, backscattered radiances are typically insensitive to aerosol composition. An important exception to this is in the near UV wavelength region, where radiances are actually highly sensitive to the aerosol interactions with background molecular radiation. So the OMI Ultraviolet Aerosol Index, or UVAI, is a method of detecting aerosol effects directly from satellite-measured radiances in the near UV. The UVAI is calculated as the ratio of the top of atmosphere radiance containing aerosol effects and the top of atmosphere radiance for a purely Rayleigh scattering atmosphere. So here I'm showing the OMI UVAI values for September 2007. Positive UVAI values indicate aerosol absorption, and we see absorbing features over desert regions and biomass burning regions. And this is because the UV absorbing aerosol types detected by the UVAI are desert dust, black carbon, and brown carbon, which is an absorbing subset of organic carbon that's produced mainly from biomass burning. Negative UVAI values indicate aerosol scattering, and these signals are most likely to be contributed by secondary inorganics and non-absorbing organics. So we've developed a framework for interpreting the OMI UVAI observations, and to do this, we use GeosChem's simulated aerosol composition in conjunction with the vector radiative transfer model VLIDORT in order to calculate the top of atmosphere radiances needed for the UVAI calculation. For our analysis, we use version 11.01 of GeosChem with the Mira 2 meteorology. So here I'm showing the results of our UVAI simulation compared to the OMI values. And for the base case, we capture absorption over desert regions. However, we fail to capture the absorption over biomass burning regions. And this is because the default of GeosChem treats all organic carbon as primarily scattering. So the scattering is overpowering the absorption by black carbon. So to combat this, we introduce absorbing brown carbon to the simulation. And we do this by deriving an effective imaginary part of the refractive index for brown carbon and use the OMI UVAI observations to constrain the magnitude of the absorption. So the bottom panel here shows the simulation containing brown carbon. And as you can see, we now reproduce the absorption over biomass burning regions. So with this working simulation, we wanted to see if we could use it to analyze trends in the OMI UVAI values in order to learn about changes in aerosol optical properties over time. So here I'm showing the mean UVAI values for 2005 to 2014, which is the time period over which we conduct our trend analysis. And we see absorbing features over desert regions and biomass burning regions, such as Central Africa. And then we see negative values corresponding to scattering over North America, South America, Southern Africa, Europe, and parts of Asia. So we conduct our trend analysis using generalized least squares regression, and we filter out scan positions affected by the OMI rho anomaly. So as you can see, there are several regions of interest between the OMI and simulated UVAI trends, and I've circled a few of them. Over the southeast US, there's an increasing trend in UVAI in both the simulated and OMI values. And then over West Africa, there's a decreasing trend in both the OMI and simulated values. But then over the Middle East and northern China, there are significant trends showing in the OMI values which aren't captured in the simulation. And so I'm going to talk about all these circled regions in more detail in a minute. But also, one thing to note about the OMI UVAI trends is that there are broad regions that show what's actually a spurious increasing trend. And we've been in touch with the OMI team, and they say it's due to possible satellite degradation in the later years of the record. So they're working with us to come up with a solution to remove that part. So over the southeast US, we see this increasing trend in UVAI values in both the simulation and OMI. So to analyze what could be possibly causing this, we calculate the changes in simulated UVAI from the trends in different aerosol species from GeosChem. So we look at secondary inorganic aerosol, black carbon, total organic aerosol, the absorbing brown carbon component of organic aerosol, and desert dust. So as you can see, this trend in UVAI seems to be dominated by a decrease in scattering SIA over the region, and we don't see contributions from any of the other species. And then over the Middle East, we see broad regions of increasing trends in the OMI values, which aren't captured in the simulation. So this is likely at least partly due to that spurious increasing OMI trend. However, I've circled in black in the OMI trends a region with significant increasing values. And this is actually due to a trend in surface reflectance over the region, which is due to drying up of the Aral Sea over the past number of years. And since this isn't an aerosol feature, we actually don't really care if we reproduce it or not. And then looking at the change in the simulated UVAI values due to the different species, we see that there's a significant decrease in UVAI due to an increase in scattering SIA. But then over the same region, we see an increase in UVAI due to an increase in absorbing desert dust. So it could be that the competing effects of scattering and absorption are canceling each other out, and that's why we don't really see a significant trend in the simulation. So then over West Africa, we see a negative UVAI trend in both the OMI and simulated values. And this is actually most likely due to an observed decreasing trend in burned area over the region, which is due to cropland expansion. And so then if we look at the change in the simulated UVAI due to the different species, we see that the simulation is dominated by a decrease in absorbing brown carbon. And this is actually the main contributor to the overall trend in organic aerosols as well. So over northern China, we see a significant decreasing trend in the OMI values, which isn't shown in the simulation. But if we look at the seasonality of the OMI trend, it mostly disappears in the winter and is strongest in summer, so this could be due to desert dust. And then over India, in both the OMI and simulated values, we see decreasing trends in the UVAI. And looking at the change in the simulated UVAI due to the different species, it appears that this is mostly dominated by an increase in scattering secondary inorganics. And so I'll leave you with some conclusions, and thank you for listening. Uh-huh. There definitely could be, but it was just more of like saying that it was kind of separate from like the other broad increases and that it can be attributed to like a real life event, so. No, we didn't really find anything over there. Okay. Okay. Yeah, no, we're not capturing that there. But it could be that there's something going on with like absorption and scattering so that it's canceling out the effect in the UVAI, and that's why we're not capturing it, because like the UVAI is like measuring the scattering and absorption, so that could be why. They do screen a bit for clouds, so it could be that maybe they don't really pick up the heavy haze days, but I haven't really looked in detail at the haze, so yeah, I don't know.
Okay. So our next speaker is Dave Ridley from MIT. Thanks, Jeff. Okay, so Colette and I have been looking at the effect of a more explicit representation of the aerosol microphysics upon the direct effect, direct radiative effect of aerosol through the aerosol optical depth changes. And so to do this, we've been using the standard bulk aerosol scheme in Geoschem, and then also the Thomas sectional scheme as well. And the sectional scheme is generally used to look at aerosol indirect effects because it's way better at simulating the aerosol number. and the CCN number and things like that. But we wanted to see how this kind of more explicit representation affects the aerosol optical depth. So this is what the typical bulk scheme does when it's trying to simulate the size distribution. We carry the mass for each of the species, and then that mass is assumed to be in a log normally distributed mode that's fixed, and that fixed mode can shift a little bit depending on the relative humidity to simulate growth. And so you have one of those for each of the species, and then you have 2 size bins for sea salt and 4 for dust because they span such a wide range of sizes. And so you end up with this kind of estimate of the continuous distribution from the aerosol. But the sectional scheme and the version we're using has 40 bins over this size range, and this allows for mass transfer from all of the different species. Between those bins, you have coagulation, condensation, and so you don't have to make any assumptions about the size distribution. And so this is something that we wanted to compare with. But the aerosol optical depth is actually dependent on the surface area rather than the mass. So if I just convert this size distribution into a surface area distribution, you see that the submicron aerosol contribute more to the surface area, but the supermicron aerosol are still important too. And then the other factor when calculating the AOD is the Me extinction efficiency. So we need to weight this distribution by the Me extinction efficiency. And so what you're essentially looking at now is the aerosol extinction size resolved. So this kind of gives us an estimate of how much each of the different sizes contribute to the AOD. So we're able to use GeosChem for both TOMAS and for the bulk scheme, so we can harmonize the emissions. And so we know that any of the differences we see are coming from changes in the aerosol microphysics affecting the mass online, or from the size distribution assumptions that we make. So I'm going to jump kind of right to the end and just compare the aerosol optical depth from the bulk scheme and from sectional scheme, and then you can see the fractional difference there. And some broad features really are that the sectional scheme has a lower AOD in general, and it's lower over the desert regions, over the ocean regions, but higher over biomass burning regions. And you can see that there's kind of over 50% difference in some locations in AOD. So you get this huge difference, and this is for 2 schemes within the same model. So if we look at the column mass burden, we see that these actually agree pretty well. So there's kind of less than 10% difference in the mass burden between the bulk and the sectional schemes. And a couple of the features are that the sectional scheme actually shows more dust and sea salt, which is kind of funny because what I was just showing is that the AOD over deserts and over oceans is actually lower in the sectional scheme. So there's more mass, but there's less AOD. So we need to look at the size distributions to really kind of understand this. So again, I'm showing this kind of proxy for the size resolved AOD, so we can see how each size contributes to the AOD. And this is a globally averaged size distribution for bulk and for the sectional scheme. And then you can see the difference between the two here. So just a few of the features that pop out. Sulfate, which is in red, actually agrees really well between the two of them. But I'm going to focus more on the sea salt and the dust, which what you can see is TOMAS is putting the sea salt and the dust at these really large sizes. And so even though there's a similar amount of mass, it's at this less optically active size relative to the bulk scheme. And so, so you end up with a higher AOD in the bulk scheme relative to TOMAS. So just looking at the sea salt emissions that go into GeosChem, this is the emissions distribution that we get from the GONG parameterization. And then if I overlay the TOMAS sea salt size distribution, you can see it follows these emissions quite well, and that you have this sedimentation. You have less of the very large particles because of sedimentation, and slightly more of the accumulation mode particles that have accumulated. So this all makes sense. And then if we look at the bulk size distribution, we see that there's quite a big difference here. And so what's happening is because the bulk size distribution is prescribed, the emissions are happening at these large sizes. So you have these really large kind of 5, 10 micron particles that are then being assumed to be concentrated at smaller sizes. And so that means you have to increase the number and therefore the surface area. So I'm showing the surface area distribution here. And so because you have this big difference in surface area, you end up with the bulk scheme having a factor 2 more AOD for the sea salt compared to TOMAS. And there's a really similar analog that happens with the dust as well. And there's potentially a way that we can fix that by shifting the bin sizes for dust in the bulk scheme. So I'm happy to talk about dust, as always. So the other thing that seems really important from this work as well is the effect of aerosol water. And so between aerocon models is about, they assume that there's about 30 to 80% of the AOD actually comes from the aerosol water rather than the aerosol itself. And so what I'm showing here now, again, these kind of size-resolved aerosol optical depth, and I'm showing this just for the dry aerosol mass. And so if we then wet the aerosol mass, between this is the bulk and sectional scheme, you see you have this like big increase in mass because of the water that gets uptaken, and then also because you don't actually increase the number, you just increase the mass. All the particles grow to larger sizes and get shifted into the more optically active sizes. So you end up with about a doubling of the AOD simply due to aerosol water. And this is kind of similar between the bulk scheme and the sectional scheme. So there are some slight differences, but this doesn't seem to explain much of the difference in the AOD between bulk and tow mass. So one last thing that I wanted to talk about is the RH, the relative humidity. And in the model, we cap this generally at 95%. And this is quite a common thing to do in models because as you approach 100%, then the aerosol water grows exponentially. And so we wanted to look at what the difference was. Say we assumed 99% instead. And we find that you get a 40% higher AOD if you cap the RH at 99%. And so there's a big difference here. And I know that some of Jeff and Jack's work, they capped it at 90%, and so people have tried different values to compare with observations. But I think we need to really think a little bit more about how we treat this in the model, because it may improve agreement over the ocean regions where generally the model is a little bit low, and so often, if we actually cap the RH at a higher value, then we'll end up with a higher AOD because the sea salt aerosol in those locations is very hygroscopic. So to conclude, we've done this comparison between the bulk scheme AOD and the sectional scheme AOD, and we find really large differences in both directions in different locations. And a lot of this discrepancy is driven by changes in size distribution between the two, rather than differences in the mass because of the aerosol microphysics. And a lot of the difference comes from the sea salt and from the dust aerosol. And at the moment, we're comparing with size distribution observations from around the world and AOD observations as well. But we're trying to understand whether the tow mass distribution at these larger sizes really does represent the actual observed size distribution better. Because if it doesn't, then it's really on the size-resolved emissions. And we need to rethink the size-resolved emissions of sea salt and of dust and how they can be altered. So thanks for your time. I'm happy to take any questions.
I'm going to do chair's prerogative and take
Go
the
for
first
it.
question. So you also showed changes in the opposite direction over downwind of biomass burning regions, right?
Yes.
Okay.
Yeah.
What do you know what the story is there?
Yeah. So.
I'm assuming you're assuming similar optical properties, right?
Yeah, that's right. Yeah, so we've harmonized all the AOD offline, so it's all calculated in the same way. Yes, you can kind of see here with the green in the OC, where you have about 10% less mass in tow mass, and I'm looking into exactly why, whether that's wet deposition differences, things like that. But what's happening is that smaller amount of mass is actually placed at slightly larger sizes, and I think it's partly to do with the internal mixing that goes on, and so you end up with more optically active OC. Versus the bulk scheme, even though the bulk has a little bit more mass in there.
Right.
What are your thoughts on having a cloud-free aerosol optical depth where you don't cap the RH?
So one of the things that I was worried about with capping at 99% instead of 95 is is a bunch of that just inside cloud? So is it kind of an unrealistic change in the AOD? But I think I might have some slide on that. But yeah, it turns out that most of it is outside of cloud anyway. There we go. I think it's here. Yeah, this plot down here. Yeah, so we find out that most of the times when the RH is at 99% is actually predominantly clear sky, and it doesn't overlap with cloud. So it seems like it is a real effect. Whether the RH is actually correct is another question. But I don't know whether, I don't think it's a good idea just to have purely cloud, like the AOD within clouds. But then also, if you want to start subtracting clouds out of there, then you've added in an extra level of complexity in that we don't know where the clouds are. So yeah, it's tricky.
So our next speaker will be Jack Kodros from Colorado State.
I'm really glad Dave went first. I have a very similar talk. But here I'm talking on the differences in the indirect effect between the standard bulk aerosol representation in geochem and the aerosol representation in TOMAS. So as Dave was saying, with TOMAS, it's a sectional aerosol scheme, so we have one tracer for every size bin, and the most complex version of TOMAS has 40 size sections. So between the 9 or so aerosol components, this adds about 360 tracers. So we have a large increase in computational burden, but we have increased information for aerosol size resolution. And the alternative to this is using the standard bulk aerosol scheme in geochem, which tracks only aerosol mass. So you have one tracer for the total mass, and you scale that total mass into normally a log normal distribution, except for things like dust and sea salt where there is some size information. So this increases your computational speed, but it's a known simplification. And to demonstrate this, I have a similar demonstration as Dave did, but now I'm showing the number distribution for 1 microgram per meter cube of sulfate mass. And so this is what you get just scaling 1 microgram per cubic meter in standard geochem. Sorry. And so standard geochem assumes that this distribution applies everywhere. But we know from observations that that isn't necessarily true. And so this orange distribution is just a hypothetical log normal distribution that I changed to be more representative of, say, a new particle formation event. So with the same 1 microgram per cubic meter mass, we have 2 very different number distributions. And we can perhaps imagine a third region, which is dominated by aqueous oxidation. So for the same, again, the same amount of sulfate mass, we have 3 very different number distributions. And this becomes really important when we want to think in terms of aerosol-cloud interactions, which are strongly dependent on cloud condensation nuclei concentration, which we can sort of take as the integral under each of these number distribution curves within the size range that I've shaded here. So clearly, the assumption that one fixed log normal distribution for each species in geochem isn't entirely physical when we want to think in terms of CCN and aerosol cloud interactions. And specifically, we kind of know from observations that different microphysical processes tend to dominate in different regions. So we want to ask how is this variability in aerosol size distributions being represented globally? And is the assumptions in geochem really representing that variability? And I should state here that we don't have size resolved measurements everywhere, so we can't specifically say that TOMAS is getting things right either. We know TOMAS has its own difficulties, but it's not entirely physical to just assume one fixed log normal distribution. So we wanted to ask, what sort of differences are we going to get in the aerosol indirect effect? And so what we looked at is the indirect effect due to just anthropogenic emissions. So we have a pair of simulations, one with all emissions on and one where we turn off all anthropogenic emissions. And that's not exactly pre-industrial state, but we can kind of say within our own heads, this is somewhat illustrative of a pre-industrial state. And when we look at the indirect effect in TOMAS, we get something like a global mean of negative 0.9 watts per meter squared. And again, in our heads, we can say that's on the order magnitude of what people get for radiant forcings from 1750. But we want to compare this to what we get from the indirect effect calculated with the standard aerosol representation in geochem. So the figure here is the difference between geochem standard and TOMAS. So the indirect effect being negative means the positive or red numbers have a more negative or a larger magnitude indirect effect in TOMAS, and the blue is a larger magnitude, more negative in geochem standard. So to explain some of this spatial variability, I've averaged simulated size distributions over the region of interest. In this case, in the first example, over South America. The dashed lines are the anthropogenic off simulations, and the solid line is the anthropogenic on simulations. And each pair of simulations has the exact same total aerosol mass, and so we're modeling the same change in mass when we include anthropogenic emissions. But in TOMAS, the anthropogenic on simulation has a smaller average size of accumulation mode particles. So this same change in mass is being distributed among slightly smaller but more numerous particles, leading to a larger relative increase in CCN compared to the standard geochem, which doesn't really have a change in the average size of the accumulation mode. So the increase in CCN from anthropogenic emissions is only from the fractional increase in mass from anthropogenic emissions. And we see the opposite effect over the North Pacific. TOMAS is kind of showing perhaps representative of an aqueous oxidation region, where now the solid line has slightly larger accumulation mode average particle size. So the exact same change in mass is now being distributed among slightly larger but less in number particles compared to the standard geochem. And it's this relative change in CCN that really determines the magnitude of the aerosol indirect effect rather than the change in mass. But just to wrap up, comparing to observations, if all you care about is sort of a long-term average or a spatial average, the geochem standard compares favorably with CCN-sized particles, as does TOMAS. So if you're only concerned with average aerosol number concentration, geochem standard does perfectly fine for you. But it's when we start thinking in terms of radiative forcings or any sort of hypothetical perturbation to your model where you're drastically changing emissions or size-resolved microphysical processes that we might want to start thinking in terms of how we're treating the aerosol size distribution. And there's also a 15-bin version of TOMAS. If you don't want to add in all 360 tracers, you end up with only 203 tracers. Thank you. No, so I'm really using the Abdul Razak and Ghan CDNC parameterization. Yeah. Cool. Yeah.
So for the size result simulation, what nucleation scheme you use?
In this, we use the ternary scheme. So in the boundary layer with SO4, NH3, and water, and scaled to whatever Dan Westervelt was scaling that to. Then bar. So, and I should say, for South America, we don't have any organic nucleation, and so that is likely sensitive to that.
Yeah, so is this, the number size distribution that you get from a bulk scheme is basically taking the standard mass size distribution and mapping it to a number.
Mm-hmm.
But the way that I've generally seen GCMs who only do bulk aerosol deal with cloud condensation nuclei population is to have a dependence of the number of cloud condensation nuclei on the total aerosol mass, right?
Yeah, some do that. Right, so some do that, some use satellites, some still use the same method that bulk geochem uses. I think the key thing here, though, is looking at how things would change in a drastically different or hypothetical model simulation rather than just the present day where we can fit to some degree a number distribution to observations and make that work. We don't really know what the size distributions would look like in a drastically different setting.
So our next speaker is Fang-Chun Yu from SUNY Albany.
Okay. I'm going to talk about the new nucleation scheme we implemented in the geochem and some of the results. New particle formation or nucleation have been found to be important to control the particle number abundance and also the particle size distributions. As you can see from this example of new particle formation, so So what's shown here is time series of the particle size distributions. This banana shape means you have a new particle formed. As you have a new particle formed, you see the size distribution change a lot. So as we see from the previous talk, size distribution change will change a number of things. Will change the number of the particles which can activate as a CCN. Also will change the size, surface area, which may be important for the chemistry uptake. So size distribution are important. In order to get the size distribution right, we need to get a nucleation process right. A number of recent studies indicate, basically the CERN Cloud project, they found ions, ammonia, amine, and even organics can help nucleations in the atmosphere. So what we try to do is add this new nuclear scheme in the geochem and try to see how they affect the aerosol formations. The first one we try is organic mediated nucleation, which is published by Le Cobono et al. In Science paper 2014. They use simple parameterization of the sulfur acid square time kind of very low volatile organic species. So that's a simpler fitting. And I think recently we found that the temperature dependency is important. So in this parameterization, do not have the temperature dependence. We know temperature generally affects the new particle formations. And we derive kind of corrections for this parameterization, which consider the temperature dependence. And I will show more results later on. We also developed ternary ion-mediated nucleations, which have been shown ammonia can enhance ion-mediated nucleations. With these ternaries, and the nucleation rate depends on sulfur acid concentration, ammonia concentrations, in addition to other parameters. And the final one we add is amine ternary nucleations. With the amines, and the nucleation rate will depend on amines constraints as well. So there are a lot of parameters may control new particle formation in the atmosphere. And of course, in order to predict the nucleation rate, we need an added scheme to calculate the precursors. So in the geochem bulk scheme, we do not have sulfur acid, but for size resolved, we usually have sulfur acid concentration explicitly simulate. Of course, we have ammonia concentrations. We add an algorithm to calculate the amines. For this one is a dimethyl amines. And we also have the low volatile bio-oxidation organic species. So we add an algorithm to calculate these schemes, these species. Then with these species, we calculate the new particle formations. So example shown here is, what's shown here is the effect of temperature dependence on the nucleation rate. So based on the original scheme from Science paper published in 2014, that's the predictions in the summer. We should see a lot of nucleation because in summer, the biogenic emission is higher, you get more organic species, you get more nucleations. But if we consider the temperature depends, the nucleation reduces a lot. So what's shown here is particle number concentration bigger than 10 nanometer. So it's changed by a factor of 2 or more in North Americans. If we compare with the size distribution measurement, what's shown here is a measurement at this site, the Duke Forest. So they have a measurement in the spring months and also in the summer months. Usually in the spring, you see a lot of new particle form, but in the summer, you didn't see much nucleations. Even the biogenic emission is higher. And based on the original organic mediated nucleation, you predict a lot of nucleation in the spring, also in the summer. So that's over predict new particle formation if you use organic mediated nucleation without temperature dependence corrections. Then when we consider temperature dependence, the nucleation reduces a lot in the summer because the temperature increasing in the summer inhibits the new particle formations. And if we compare with the number measurement, so in the spring, it seems the temperature dependence does not affect a lot, and it's close to observation in terms of number concentration. In the summer, without the temperature dependence, the model often predicts the number concentration. Of course, also change the size distribution of particles. So we feel the temperature dependency is important. We also look at the ternary ion mediated nucleations. It's a new scheme we have been developed. We give here one example about the measurement taken in the Discover AQ 2011 in the Baltimore regions. This is in the summer aircraft measurement, also have the surface measurement. Here, just one example. This is the aircraft measurement at the different kind of altitude. You see in these 2 days, you see even in the summer, it's July, end of July, you see a lot of new particle form, even in the summer. And new particle formation definitely contribute to the large particles when they grow. And that's the model simulations with the geochem APM when we consider the ternary nucleation. We capture this day nucleation events, but it seems we didn't capture any of the nucleations for the previous day. And when we look further about the precursors, what is shown here is a number of precursor S2. Let's just zoom in for sulfur acid. Gas concentration, both there you'll see have sulfur acid gas. For the organics, you also have the organics. But we found that somehow the model predicts the ammonia concentration around the PBB level on this day, but kind of go to zero, drop to zero on the previous day. And when we use the ternary nucleation, we basically didn't see any nucleations. So we feel ammonia concentration is important. In the model, we need to get the ammonia right in order to predict the impact of the ammonia or ternary nucleations on new particle formations. We also did some calculation for the amines. So amine also have been observed to be important for nucleations. What is shown here is just one example. For the amine nucleation in the global scale, we found over East Asia, amine nucleation could be important, especially over China. So nucleation rate could be pretty high, also important. To summarize, we add new particle formation schemes in the geochem model and try to evaluate their importance. We found the temperature dependency is important. A lot of models use kind of simple parameterization, which do not have a temperature dependence, and we found that that's important. We found that ammonia have a strong effect on the ion-mediated nucleations. That's bring up questions that we need to evaluate the model ammonia gas concentration simulation and to compare with observation and maybe even improve. We also found that ternary nucleation involving amines could be important, especially even over East Asia. And that's bring another question about the importance for the emission inventory for amines and how to simulate amines. So I will stop here. Thank you for your attention.
Silveren gave a talk on how there's this reduced uptake of ammonia to ammonium that would free up more ammonia for the gas phase.
Right.
So have you thought about considering trying to combine that to see if
Yeah, I think that's could be very important. Actually, I think next talk again will also mention that. The uptake change will change the ammonia concentration, and that's what changes that. Another thing that we are looking at is isotopia. Isotopia have certain assumption. Under certain conditions, the ammonia just go to zero. They assume all ammonia get into the aerosol. And I think that's probably some kinetic process, maybe limit that. So I think in early study, we only focus on ammonia in the aerosol. But if the ammonia is important for nucleation, then we need to look into ammonia in the gas phase. And that could be important uptake and other process, yeah. Yes.
I was curious in your amine simulation, like if here we should add amines to the model.
Right. Yeah, that's a good question. So I think that amine, basically, we do not have information, no emission information. But there are some estimates in the literature. They found amine emission generally is 1% of ammonia. Around, there are some estimates. So in our simulation, we assume 1% of ammonia emits amine. But their lifetime is different. Amine have much shorter lifetime because of quick oxidations and also uptake. So we consider emission, we also consider oxidation of the amine and uptake. Then you get a balance of amine in the atmosphere. We compare with some measurement, we found that we generally under-predict the amine concentrations. So we may under-predict the nucleation here because we under-predict the amine concentration. But we do not have a lot of information, but that's something I think we can look into that.
Would your amine concentration be correlated with gas phase ammonia, and could you use satellite observations to evaluate your model?
it's possible, but it's hard. I mean, amine concentration usually in the PPT level. Ammonia concentration ppb or sub-ppb level. We're looking at that. Actually, when we use 1% scale, it's not exactly right. So agricultural emissions dominate the ammonia emission, but it means it's not. So we are looking at that based on more detailed observation. We found a different emission of ammonia may have different percentage of amine associated with that. So not necessarily, but need more information to look into that. And amine can also affect the chemistry as well. When you have amines, they affect the chemistry, equilibrium stuff.
Okay, thank you. Our final speaker, our final full-length speaker this morning will be Gan Luo, also of SUNY Albany.
Okay, thank you. I will introduce our work about the aerosol macrophysics and its impact on heterogeneous chemistry. Okay, here. Yeah, it's known that aerosol is very important for atmospheric chemistry. It can impact atmospheric chemistry via the change of photonize rate and via providing the surface where the heterogeneous reactions can occur. And it's known that the dominant heterogeneous chemistry in the troposphere is the reactive uptake of N2O5. And due to the change of N2O5, it will change the producing of nitric acid and the removing of oxygen of nitrogen from the atmosphere. In current geochem, it's using the bulk aerosol information to calculate the heterogeneous chemistry. Because in the past several years, we developed the size-resolved aerosol macrophysics in geochem. It can provide very good information about the size information, surface area information, and the mixing information. So in this study, we try to switch the bulk aerosol to the size-resolved aerosol to see how aerosol macrophysics impact heterogeneous chemistry in geochem. This slide shows the method we used to calculate heterogeneous the uptake rate. The first formula is the equation to calculate the uptake rate. It shows it can be divided into two kind of effects. One is called the size effect. It means due to the change of aerosol surface area, the uptake will be changed. Another effect is called the mixing effect. It's due to different aerosol has different ability to uptake N2O5. So when you considering different aerosol components, it will impact the uptake parameter. And the second formula is the formula we used in our model to calculate the gamma of a secondary particle. Because in our model, we use a secondary particle to represent the secondary produced particles, such like the sulfate, ammonia, nitrate, and also some SOA. And we designed three cases. One is called the old one. Old one is use the bulk aerosol to simulate the heterogeneous chemistry. The second one is called the new surface one. It means that we only change the surface area. We use the APM simulated surface area to replace the bulk surface area to study the size effect. And the third one is called the new OR. It means that we considering both size effect and the mixing effect. This picture shows the changes, the relative change of N2O5 over three regions. The red line represents the changes over the North Hemisphere. The blue line represents the changes over Tropica. The black line shows the changes over South Hemisphere. And it's clear that over South Hemisphere and Troposphere and the regions, the relative change of N2O5 are relatively slow. But in North Hemisphere, the change in winter time could be very large. For example, for the surface effect in wintertime, the change can high up to 80 to 90%. And if we considering both size and the mixing effect, the change could high up to 170 or 80 percentage. Here shows the example of the changes of N2O5 at the surface during wintertime. The first line is the relative change of gamma. It means the uptake parameter. For the left column is the change only considering aerosol size. So it means the aerosol mixing effect is very small. And for the right line is the case considering both size effect and the mixing effect. You can find that it shows that the gamma didn't change too much on the left side, but the gamma could be changed a little bit larger at the right side. For the domain average, it can help to it's about 18%, and at some regions it could help to 50%. And the third line and the second line and the third line shows the relative change and the absolute change of N2O5. It shows that due to the surface impact, the relative change of N2O5 over this domain could help to 87%. And if we considering both of the effect, the change can help to 175. And the absolute change could also be high up at some regions up to 100 ppt. It's know that N2O5, the geochem simulated N2O5 sometimes is always lower than the observation. I think our simulation provided maybe a positive direction to solve this kind of problem. And this slide shows the impact on nitric acid and NO2. As we said before, due to the enhance of N2O5, the production rate of nitric acid could be reduced due to the reduced uptake of N2O5. And due to the, because the sink of the N2O5 has been reduced, so the NO2 concentration could be enhanced during this period. And we also compare the NO2, the column NO2 concentration with satellite. The left top line is the satellite retrieval result from the GeoME2. And the right top is the original result from GeoChem with the bulk aerosol heterogeneous chemistry. And it's clear that the column concentration of NO2 is pretty smaller compared to satellite retrieval result. And after we use the size effect and the size and the mixing effect, we found that the concentration of NO2 has been significantly enhanced at some region, especially over Europe. And the table shows some the number of the average number in the black box. And we also studied the impact on nitrate, ammonia, and ammonia. And we found that the global change of these aerosol species are pretty small, but at some region, the difference can help to 30 to 40%. Here is my summary. Yeah.
Can you pinpoint what is it in the aerosol microphysics that hinders the uptake of N2O5 compared to the bulk?
The first is the size, the surface area has been changed. Another is that when we calculate the uptake parameter, in GeoChem, we just use 5 gamma volume for one for the sulfate and BCO, sea soda, and the dust. And when we calculate, we considering for sulfate, we change it to this formula. We use the mass weighted to say, so when we calculate the the volume of second particle, the gamma volume, we considering the mixing of sulfate, nitrate, ammonia, and the nitrate effect has been included. And we also included the impact of organic on this gamma volume. But due to some recent papers says that there are also some uncertainty amounts to the volume of organics. Yeah.
Okay, so now we'll move to the 1-minute poster. 30 seconds. 30 seconds. We're not at the GRC.
Thanks.
In the summertime Arctic, aerosol number is strongly controlled by natural sources. We're using geochem to mass to better understand how natural sources shape this aerosol size distribution typical of Arctic summer. These simulations appear to be missing something, possibly organic vapors for particle growth. If you're interested to find out how we can improve our simulations and to further discuss the role of natural sources in the Arctic summer, please drop by my poster.
So we are all generally aware that there are oceans, and most of us know that the oceans can emit volatile organic compounds like dimethyl sulfide or possible other VOCs. And then some of us might think about what happens to those VOCs, like oxidizing to lower volatility material like MSA. But very few of us think about what happens if you put these lower volatility materials into the sized resolved portion of GeoChem. So if you'd like to know that and possibly more, come to my poster.
Hi everyone, I'm Yana Zhang from SUNY Albany. My work was mainly about to connect the global GeoChem API model to regional WolfChem API model. We use the GeoChem API model to produce a real-time dust background to drive the WolfChem model. And the results show that this dust boundary condition has a very important impact on the WolfChem's dust and cloud ice simulation. So if you are interested, please stop by my poster. Thank you.
Okay, I'm Jin Xubang from Peking University, and my work is focused on the factors affecting aerosol radiative forcing. In our work, we divide the radiative forcing into 5 parts, and we found that, except for the socioeconomic factors, the atmospheric factors also play a leading role in some regions. Okay, for more details, welcome to my poster. Thanks.
So we develop a GeoChem simulation for brown carbon and investigate its radiative impact. In the past few years, the problem of simulating brown carbon is we do not have direct and continuous measurement to evaluate. Thanks for the DC3 and CCAS4 campaign, now we can test our assumptions to such observations. So for more of the details, please come to my poster.
And Jeff for chairing this session. We will now have a group photo, and Brown Massacres in the back will lead us to the spot where we'll take the photo. And we will reconvene at 1:30 here for the sources and sinks and transport session. What room is what?
What room is the GCHB clinic in?
The GCHB clinic is here. Yeah, the GCHB clinic will be at 12:45 here.
one of the things we found is that when we moved to Pemco, the initial files were putting in as teragrams of NO2 with big red dots. And the conversion from NO2 and NO was being made. So European emissions are NO2 divided by NO too high. So they come in as NO2, but we emit as NO. So we just have to apply that conversion, but we'll go back, but also like the VOCs have been the same since I think year 2000. So we're going to go back and repost the same thing, and have to stop instead of VOCs. I will. It's all done when we're here. You know, set Thomas a task, he can do it in the morning, and it'll all be done before.
Standard as Europea, doesn't it?
lunch break or?
Yeah, to give you a picture.
Oh, okay. Because we should probably give the AV system a rest. Oh, yeah, yeah. No sense running these for